Okay, we are starting the second to the last batch of materials, so we are almost done. Right now, we're going to talk about conditional expectation. I'm going to start out following the supplemental notes, and then we're going to shift back to the textbook section 7.5 for a couple of examples. Okay, so conditional expectation. Let's say we have two random variables. Then, if x is discrete, then the expected value of x given y equals little y is equal to the sum over the range of x. So I'll say the sum over little x and the range of x times the conditional mass function of x given y. Okay, so it looks like just your ordinary sum for the expected value of a discrete random variable, but it's got the conditional mass function in there instead of the regular mass function. Okay, now, if x is continuous, then the expected value of x given y equals little y is the integral from negative infinity to infinity of x times the conditional density of x given y, integrated dx. And again, it looks like the ordinary definition of the expected value of a continuous random variable, except instead of just the ordinary density of x, you have the conditional density. Okay. Now, the expected value of x given y equals little y is a function of y. Okay. So if you look back up in those definitions, in one case you sum out all the x's, the only thing left is a little y. In the other case you integrate out all the x's and all that's left is a little y. So when you're computing this thing, you're computing a function. It's a function of little y. And we could give that function a name in particular examples. So when we go into a particular example, we'll often name that function just to make it easier to talk about. So let's say I named it g. So g of little y is the expected value of x given y equals little y. Now there's another kind of conditional expectation, and that's the expected value of x given y, where we don't have an equals little y in there. If you don't have the equals little y, what that means is you take that function g and you plug in the random variable capital Y into that function. G of capital Y. That's what it is. Now, g of capital Y is a random variable. So the expected value of x given y is a random variable. So now might be a good time to pause and replay this and think about it for a minute, because this is a little mind-bending for some people, or it might be a good place to bookmark and come back to after you've seen some examples and make sure that you understand what's going on here. These are both objects, so the expected value of x given y equals little y, that one, and the expected value of x given y without an equals little y. Both of those are going to be very important, and you need to know how to work with them both. You can't just say, okay, this one confuses me, so I'm going to focus on the other one. You're going to need to understand them both. So maybe, yes, bookmark this spot, know where to come back to it, and take your time processing this. And like I said, we're going to look at examples, and hopefully that will bring some clarity to it. In fact, let's look at an example right now. So this is, I'm in my notes, the supplemental notes. I'm doing this example. This is example 4.1 in the notes, the supplemental notes. Okay, so in this example, let's see what we've got. Um, hmm. Oh, here it is. Okay. So in this example, I have a pair of random variables x and y. They are jointly continuous. The marginal of x is 1/6 x cubed e to the negative x if x is positive, and it's 0 otherwise. And the conditional density of y given x is 3 times x minus y squared over 8x cubed if the absolute value of y is less than x. It's 0 if the absolute value of y is greater than or equal to x and x is positive, and it's undefined if x is less than or equal to 0. Okay. And these objects are actually coming from an earlier example in the notes, example 2.1. In example 2.1, there was a different question that was being asked. You can look at that yourself. Here what we want to ask is, we want to find the expected value of y given x equals little x, and we want to know the expected value of y given x. Okay, so we'll just start off. So with the first one, we have the expected value of y given x equals little x. So y is a continuous random variable, so it's going to be an integral. And we want to integrate little y times the density of y, but we want to use the conditional density. Oops, it's y given x, not x given y. Sorry about that. Integrated dy. Okay, now this thing, the integrand there is undefined when x is less than or equal to 0. So that means my conditional expectation is undefined if little x is less than or equal to 0. So we want to just consider x greater than 0. So what happens when x is greater than 0? Then we have the integral from negative infinity, well, not negative infinity to infinity. All right. If x is greater than 0, that density is only non-zero when absolute y is less than x. So we're only going to be integrating dy from negative x to x. And then on that interval, the conditional density is 3 times x minus y squared over 8x cubed, and we integrate that dy. And I'm going to skip the calculus. You can do the calculus there. X is a constant, y is the variable of integration, and you're going to get negative x over 2. Summarizing our answer then, we get that the expected value of y given x equals little x is equal to negative x over 2 if x is positive, and undefined if x is less than or equal to 0. So that's the first part of the problem. Then the second part of the problem is to figure out, well, then what is the expected value of y given x if we don't have an equals little x? Well, in that case, what we're supposed to do is plug the random variable capital X into this function. Okay, so then we look at that function, and one thing that might stand out is that, well, that function is undefined when x is less than or equal to 0. So capital X is a random variable. It's just going to be some random number. What if randomly it happens to be negative? Then it won't make sense to plug it in. But that can't happen. You see, if you go back and you look at the density here, the marginal density of capital X, it's supported on the positive half line. The probability that capital X is negative is 0. So, and it's always going to work out like that. Even though this function here might have portions where it's undefined, capital X, the thing, that you're conditioning on here, that will never take values in the places where this function is undefined. It can't happen. It's always going to work out that you can plug X into it. And then when we plug X into it, then we don't have to worry about the undefined part, and we just have that the expected value of Y given X is negative X over 2. Negative capital X over 2. So this thing, let's get a blue, that thing, that's a function, right? A function of little x. That thing, that's a random variable. Two different kinds of mathematical objects. And it's important to understand the difference and the relationship between the two, and how you can figure out which is which and understand all this notation. Okay, so there's an example. Now, because the expected value of y given x or x given y is a random variable, we can ask, well, what is its expected value? So in general, we could want to know what is the expected value of the expected value of x given y. All right, well, first of all, how would we write that down? Well, so let's say x is continuous, right? Then the expected value of x given y equals little y is the integral of the conditional density, of x times the conditional density of x given y. Okay. And we can call that function g of little y. And then the expected value of x given y without the equals little y, that's g of capital Y. And so the expected value of the expected value of x given capital Y is just the expected value of g of capital Y. And then we know how to compute the expected value of a function of a random variable. We've got the integral from negative infinity to infinity, g of little y times the marginal density of capital Y. But where's g of little y? Well, it's right here. So that's the integral from negative infinity to infinity of the expected value of x given y equals little y times the density of y. So this thing right here equals this final integral. Well, then where would you go from there? How do you compute it further? I'm not going to go through the details here in the lecture. They're in the notes that I wrote, the full derivation. And when you go through that derivation, you end up getting that this is just the expected value of x. This is a fundamentally important result in probability theory. The expected value of x given y is equal to the expected value of x. That is a very succinct, compact way of writing this fundamental theorem. In practice, when we use it in our class here, we're going to use it in a couple of different forms. So when x is continuous, we just saw above that we can express this fact and say that the expected value of x is equal to, and then this here, the left-hand side, we found could be expressed with this integral. So it's equal to the integral from negative infinity to infinity of the expected value of x given y equals little y times the density of y. And actually, I need here, I actually need y to be continuous here. So here I need y to be continuous. And all of this same stuff would have worked out, what I'm showing you, even if x were discrete, as long as y were continuous. So let me change this right here. I really need a pen that works. I really need y to be continuous, for this to be the expression. If y is discrete, and again I won't go through the details, but it's completely analogous to what we've done here, then this main assertion says that the expected value of x can be written as the sum over all little y in the range of capital Y of the expected value of x given y equals little y times the marginal mass function of little y. Okay. So these forms of this expression are the ones that are going to be useful to us in solving problems. Okay, I'm going to do an example, but let me stop and start a new video.